and the hydrogen of hydrogen cyanide. The other mode of interaction is hydrogen bonding between that hydrogen of pyridine ring and the nitrogen of hydrogen cyanide. But actually, what we found to be lowest energy structure was a little bit strange structure in which we have nitrogen interaction. And this was very strange, and it was the lowest energy structure using D3 and also M06. So, how we can have such structure? The answer can go to the charge distribution. The nitrogen of pyridine radical cation is actually positive, so that's why it interacts with the negative nitrogen of hydrogen cyanide. So that's why this structure is the lowest energy structure. And when we extended that study to have the other hydrogen cyanide additions, we can see here that the second one is going again to be external solvation, and the third starts to have the internal solvation structure and continues as well. So now we ask another question about the pyrimidine radical cation. Will it interact similar to the pyridine, or it would have different way? So we had that study of pyrimidine radical cation, and it adds up to 4 hydrogen cyanide at low temperature, and we can see here that the interaction happens through hydrogen bonding rather than this nitrogen interaction. And the reason is, again, the charge distribution. These 2 hydrogens here are the most positive charge centers on the pyrimidine radical cation center. And we can see here that the interaction is again hydrogen bonding. So we extended the additions to the 4 additions. We can see here that from 1 to 2, we start for the first time to see that the internal solvation happens from the second step, and it happens to give that symmetric structure. We have that symmetric structure stays at 3, and at 4 we have internal solvated structure. So now we want to go to part 3, or before that we go to the summary here. We compare benzene to phenylacetylene to pyridine to pyrimidine. We find that all of them are going with hydrogen bonding, except this one, which is pure ion dipole interaction, and most of them are weak interaction. And when we compare that to the protonated pyridine, we see that the interaction is stronger in case of protonated pyridine, because this charge center is a little bit more positive than all the others. So the third study is actually still in progress, in which we had acetylene radical cation interacting with hydrogen cyanide. So we are asking a question here: if 2 hydrogen cyanide to the acetylene would give the pyrimidine radical cation, and 1 acetylene with 1 acetylene neutral and 1 hydrogen cyanide will give pyridine. So that's a question that is very interesting to try to answer. So we started by having acetylene radical cation and helium only in the cell. Once we have hydrogen cyanide in the cell, we can see here that we have 2 kinds of products. First kind is the adduct formation, which is C3H3N, happens from acetylene to 1 hydrogen cyanide, and this adds 1 more hydrogen cyanide to give C4H4N2, which actually we're interested in because it has the same molecular formula as the pyrimidine, and it has shown another addition again here at room temperature. To study the strength or the stability of that C4H4N2, we raise the temperature, because if it was pyrimidine or it has pyrimidine structure, it would be stable at high temperature. So we raise the temperature up to 625 Kelvin. We found that it stays there. So qualitatively, we can tell that we're forming pyrimidine. So if it was pyrimidine, it would react like pyrimidine. So here we study the thermochemistry measurements, in which we have, here we have the thermochemistry measurements, in which we have the acetylene interacting with hydrogen cyanide at low temperatures, and we can see here that this is very similar to what we have seen in case of pyrimidine radical cation. So acetylene interacting with two hydrogen cyanides actually forming something similar to the real pyrimidine. And when we compare that values that obtained from both band hop, we found that they are matched really well. So this value here is pyrimidine formed from acetylene to hydrogen cyanide, and the second value is actually real pyrimidine. So they match really well within the experimental uncertainty. So in conclusion, the first part showed the interaction of pyrimidine radical cation with water to be hydrogen bonding, and it actually has binding energy of 9 to 12 kilocalorie. Afterwards, this study was extended to the protonated pyrimidine, in which we have seen stronger hydrogen bonds with water, methanol, and acetonitrile. So here we have seen the structure and binding energy measurements. Also, we have seen something very interesting, which was the protonated water clusters and protonated methanol clusters. We didn't see that at all in case of acetonitrile, because we have seen here that we had dissociated proton transfer that was effective in terms of pyrimidine, protonated pyrimidine water form and protonated pyrimidine methanol 3. But it didn't happen in case of acetonitrile because of the blocked structures that acetonitrile has. Then the second part has the interaction of hydrogen cyanide with different aromatic compounds. So it starts by the benzene, and we have seen that we have ion dipole interactions, and we extended that to the phenylacetylene, in which we wanted to see the linear hydrogen cyanide shape. So we have seen hydrogen bonding interaction happens in case of most of the aromatic cations between the hydrogen cyanide and the aromatic cation. And when we extended that to the pyridine radical cation, we found that it forms a new type of interaction, which is N-N interaction, and we attributed that to the difference of a charge that pyridine has positive nitrogen, while hydrogen cyanide has negative nitrogen. When we tried that with pyrimidine, we expected that to behave a little bit similar, but actually it formed regular hydrogen bond. Last part, we still investigating the interaction of acetylene radical cation with hydrogen cyanide, and this study is still under progress, and it showed us that we have similar formation of pyrimidine radical cation from one acetylene and two hydrogen cyanide, and we expect to have a barrier in that transformation from that associated complex to the covalent structure, and this is expected to come from the excess injection energy that we have in our studies. So by that, I would like to thank all my group members. I will start with my advisor, Dr. Saint Michel, who is just supportive and helped me a lot with many ideas, and without him, I couldn't do this work. I would like to thank all the group members. I start with my former postdoc, Paul Momo. He's now at Agilent Technologies, and he's senior scientist. He's doing very well. And we have here Dr. Abdurrahman Soyman, who is with us, and he's my senior colleague, and we work together on many projects. Then we have Pramod Sharma. He stayed with us for a year, and he was very helpful. We did a lot of work together. Then Victor was here and left, and Ahmed stayed here. Dr. Sheikh, Kwame, Barry, Abdullah, Hani, Natalie, Khaled, Men, Lila, Cyril, and by that I would like to thank you so much.
Questions? Anything you want to know about hydrogen bonding with organic animals?
Yeah. So is the next experiment in that last piece where you have two hydrogen cyanides and the acetylene? Are you going to do the mobility experiment?
Exactly. So we try to get co-expansion. So we have the acetylene going through the hydrogen cyanide, and we expand that together. So they are expected to have such a structure, which is we should see the pyridine and pyrimidine.
So why didn't you do it?
Well, still, I did not work, so still we have time. So just we need to get that study. So first we select the pyridine and pyrimidine. So we need to dissociate that. We raise the injection energy. So if it was forming pyrimidine, it would dissociate like pyrimidine. And it also would have similar mobility to the pyrimidine. Yeah. So this mobility in particular would be different from the linear pyridine or pyrimidine. Yes.
Have you calculated the mobilities yet?
Well, the calculated?
Yeah, because, I mean, you got to do the experiment too,
Yeah.
but you need to get the, the mobility calculated for the different possible structures of the purity plus two HCNs to find
Well,
out
yes, we did that.
which structure.
Yeah, but we still need to do the experiment.
You already measured the pyrimidine mobility, the
Yes.
real pyrimidine.
Yes.
Right.
Dr. Ratan is saying you should think of other structures that's not cyclic, not covalent. Basically just HCN plus acetylene. And so you
Well, we did not do that yet.
yeah.
Yeah, we still need to do that. Yeah.
And just in terms of the calculation of the structures, I'm just curious how long you set them up in the, the initial geometries where you expect the bonding to be.
Well, we basically tried all the structures, all the possible structures, and we run all of them, so we let them to relax till we see what is the lowest energy structure. And we compare that with the experiment as well. So we need to have the lowest energy structure, and it needs to be comparable to the experiment.
Right.
Yeah.
And about how long does each optimization of structure take?
It depends on the step. The first step usually takes like less than a day, but when we go to 4 or something, it might take 3 days.
Okay.
And
How,
also
how
depends
many,
on the
how
level
many
of the
solvent
yes,
molecules?
it depends on the level of the CO2.
Yeah, yeah.
Other questions? Dr. Scott?
You were talking about making polyaromatic hydrocarbons or nitrogen substitute. And your mechanism seemed to be mainly oriented along taking a hydrocarbon cation and then treating it with something like hydrogen cyanide. How likely is another pathway? That is, taking maybe a fairly abundant gas-phase cation like N+, and having it incorporate itself into an existing polyaromatic hydrocarbon?
Well, the theory expected that pathway to be more relevant. So they studied that benzene, for example, they studied it to be losing one hydrogen, and afterwards it adds nitrogen to it, like starting from benzene and hydrogen cyanide. So theoretically, they said that this pathway is very possible. So, and also what we have here is we have acetylene radical cation, which is very abundant as well. And we have the hydrogen cyanide, so we take like 2 abundant species. So the acetylene is abundant as ion and the hydrogen cyanide is abundant as neutral. So we expect that to be at least possible route of the formation of pyrimidine on meteorites or something like that. Yeah.
So you have to stay with HCN
Yeah.
and acetylene.
Yeah.
You discussed the bond between negative nitrogen and the positive one on the ring.
Yeah.
Did you ever see water attached to that side also? Because negative oxygen and water would, at least in principle, would seem to have the same affinity.
Well, pyridine water interaction was studied before in our group, and it showed like this conventional interaction is actually possible, but it's not the lowest energy structure, and it's different from the experiment too. So in case of the experiment and the theory, they expected to have dystonic ion. Dystonic ions mean one hydrogen moves from the para carbon to the nitrogen, and the interaction happens there. So this was the case in case of pyridine water.
Other question? Kwame? Don't you want to ask any question? Did I surprise you? Okay, so actually Ahmed is going to leave us soon, right? So he's going to work for Professor Graham Cooks at Purdue University. So, but he promised before he leaves, he's going to finish the missing link.
Yeah.
So if we don't have any more questions, let's thank Ahmed again.